Starting this week, we're going to talk about hardware, how to build a computer. This is different from the last 6 weeks where we had some exposure to programming to know we convert problems into a bunch of codes, and at the end of the semester, we'll see how those codes get executed on a modern von Neumann computer. And throughout the 6 weeks, hopefully, we got some feeling of the notion of system building, the modular system building approach. You take abstraction of, let's say, a function, some software construct, and you use that abstraction, the primitive that you just wrote, in building a bigger system. And that same principle applies in hardware. So we're going to look at hardware building blocks. And we'll start from the bottom up this time. We're going to look at transistors. And we will see that, in fact, transistors are essentially just some slightly more complex electric circuit that you've already visited before. And from the transistors, we'll build logic gates, we'll build functional units, and eventually the computer. Of course, this is why do we do this? It's not difficult to see. If we only have a computer and we don't have any circuit, we can do abstract computation, but how do we control the world? How do we have actuators? And that clearly needs some sort of interface between an abstract computer that produces zeros and ones to the outside world. And these models are very, very useful. They help you in all kinds of situations. Heat transfer, for instance, is a dual problem for electrical circuits. The same law that you learn here can be applied there. Here's a motherboard or a circuit board, really for simple, like this type of little robots, if you wish. They have a chip inside. That's the thing that we're gonna, in the end, understand. This is a computer, a central processing unit. They have all kinds of power supply and stuff to support it. And in the end, you can have output of a board such as this connected to other stuff. In this case, some of that is used to control a motor. And you can imagine having a little robot where the motor or the motors, more likely, are controlled by your code that takes the input sensors, read them into abstract numbers, process them, and send out controls to the outside world. So circuit is very useful. You've seen things like that. If I have a resistor, I have a voltage, can we figure out the current flying in this circuit? And that is governed by Ohm's law that you already know. If I have more than that very simple circuit, for instance, if I have two resistors connected in series, you probably know that already. You've probably learned some sort of equivalence model. Okay, voltage is I times the equivalence of a series resistor, which is merely the sum of the two. And you've probably dealt with parallel equivalence. What about the two resistors having the same resistance? And you can convert that into a single resistor of a certain value, in this case 20 ohm, and then you can subsequently simplify this by adding the series resistors that's effectively connected to that equivalent resistor, and then you found out that you have another 40 ohm resistor, and so on and so forth, and you can sort of see through this circuit. Okay. But what if the circuit is slightly more complex? There's no apparent way to do your conversion, to apply your equivalence model. I mean, those of you who've learned this a little bit perhaps know you can convert a Y connection into a triangle, but that's beside the point. We can always make things more more messy for you. So how do you solve problems like that? Okay, and in particular, we had this discussion. Okay, let's look at this very simple thing. How much current is going to flow out of the voltage source? If you haven't done this, pause and think about it, right? So we had some, it's very common for people to have developed some intuition, and these intuitions are probably helped formed by your everyday experience. If I'm connecting a battery to a device, that battery must be supplying current. That's how we get energy. So there's no way this 1 volt battery is gonna have a 0 current flow, because that doesn't work. It's not that really it doesn't work, it's that it's it's not something that we've seen a lot. It's merely unfamiliar. And in this particular case, that's exactly what the voltage source is going to supply, 0 amp. How so? It's really this circuit is controlled or is constrained by a whole bunch of laws. We call them laws. Some of them are perhaps a sort of empirical observation, like Ohm's law. If we have a resistor, we keep on looking at the voltage across it, the current through it. We see that they're linearly related to each other. At least at the very beginning, we don't know why. Perhaps we don't care why. So there are laws like that. There are other laws that are probably more intuitive from a conservation point of view. If I'm sending out 1 amp of current, what that really means is in charge, in terms of charge, I'm supplying 1 coulomb of charge per second. Now what do you think, first of all, that charge is? It's a collection of charge-carrying particles. In most of the circuit that we deal with, the charge-carrying particle is the electron. So really, it's the joint action of, 10 to the 19th, that level of number of electrons that we summarize into amps level of current. And these electrons, they don't disappear. They flow in your circuit, they don't go outside of the circuit. If they do, then you draw that into your part of the circuit. Suppose you have a leak, you have a wire that is not insulated and it was touching ground. Then what you have to do is to model, to change the circuit diagram to reflect what is really happening, and then solve that problem. Then you see what's going to happen, right? So in this case, what are some of the constraints placed? An ideal voltage source places a constraint that says the 2 sides of the voltage source need to have 1 volt of potential difference, 1 volt of voltage. The current source on the other side says that there needs to be 1 amp of current flowing from one side to the other side of the current source. Okay, and Ohm's law says if I have a device over here, the voltage across this device is this times the current through this device. Okay, and some of the other laws that we're going to look in detail are what I call conservation laws, if you wish, or invariance laws. So we know already the voltage across this, we'll see why in KVL, the voltage across this is 1 volt. That's dictated by the current, the voltage source. Therefore, there needs to be an amp of current flowing this way, 1 amp. And we also know there's an amp of current flowing this way. So if the voltage source is supplying anything, then where does the current go? So the only logical thing in this case, there is 0 amp. It's not discharging. And if we reduce this, let's say to half an amp, then we will get a 0.5 amp of current coming from the voltage source. Okay? It depends on the circumstance. If we conversely change this to 2 amp, then 1 amp is going to keep on flowing in that way. And we're in fact charging the voltage source. The voltage source is not a battery. I mean, battery is a very close model in the real world of what our ideal voltage source is. Your common battery has internal resistance, has current supply limit, whole lot of things. An ideal voltage source says the voltage has to be 1 volt. I don't care about anything else. The current can be 0, can be positive, can be negative, doesn't matter. Okay, so KVL. What is KVL? We know what a voltage means. It's or if we don't, it's we're familiar with it now. We measure it. It's a fundamental property of the circuit. At any element, at any point, 2 points in the circuit, there's a potential difference, a voltage. This is sort of like temperature that you are familiar with. In the room, there could be lots of difference in absolute temperature. So there is temperature difference. So the voltage that we're talking about is usually the voltage difference or the potential difference. So V4 here says point A, the voltage is V4 unit or volts higher than D. And the V1 says, okay, we don't know. Usually there is a polarity. We have to define what we mean by V1. So let's say this is the negative side, this is the higher side. Then we say this side is V1 volt higher than that side. And if V1 is a negative number, then the right-hand side is lower. So V1 is a scalar. The polarity is something you arbitrarily define. You say, okay, this is negative side, this is positive side. The V1 simply means the potential of here minus that. If you flip the polarity, then it's VA minus VB. So V1 is really, according to the current polarity, is just the potential. We sometimes also use V to represent that, minus VA. So what is KVL? KVL says since there's a whole bunch of potentials, okay, D having its potential, A is V4 times higher than that, or V4 volt higher than that, B is V1 unit higher than that, and if we keep on going, we can have polarity set. And if we go around the circle, what do we see? If we start from D, we go to A, go to B, go to C, and come back to D. D, at any moment, a snapshot of the circuit, every point has its voltage, has its potential. Then if I go around it, my potential is VD back again. But in this trip around the circuit, I experienced voltage difference. It was V4 volt because that's the difference between VA and VB, positive V1 volt. I'm increasing V1 volt because that's the difference between VA and VB. So if you go around the circuit, your potential didn't change, then all the cumulative voltage change has to be 0. Okay, that's one way of saying you go around the circle, the voltage cumulatively add up to 0. Another way of looking at it is really just a different way of experiencing it. If I go to VB in one way, the voltage difference has to be the same as if I go there another way. Why? Because going from D to B, I'm going to see a potential difference of VB minus VD in either way, in way A, or sorry, route 1 or route 2. Okay, so therefore V4 plus V1 is the potential difference that I see for cumulative voltage on trip 1 or on route 1. On route 2, it's V3 plus V2. They have to be the same, which really is just another way of writing that equation over there. This is rather straightforward, okay? Which basically says this: if you keep on walking and you go around and reach the same point, you cannot possibly have, by the same point, you have the same altitude. You cannot say, I go around the country, I flew from one city to another, yet another one, and when I finally come back to the initial city that I flew from, the cumulative altitude difference that I've seen, that cannot be anything but 0. It doesn't make sense to be anything else. So that's KVL, Kirchhoff's voltage law. So any circuit, we look at it, we go around, we say, oh, look at these. Even though I have 4 voltages, they cannot be completely independent. There's a rule that says if I add them up, they have to be 0. So they're constrained. The degree of freedom is limited by one loop, in one loop. So we did this in class. If you haven't done it, you should pause and try to answer the question. How many equations can you write according to KVL? Is it 3? Is it 5? Is it 7? Is it more? Well, it's fairly straightforward to spot the 3 loops, right? Oh, here's a loop, here's a loop, here's a loop. But there are other loops. What if I use a different color? What if I'm going around, as long as I'm starting from one place and I go back to the same place? How about I go along this line and back to the same place? Isn't that a loop? It is a loop. So if I keep on doing this, how many loops there are? And you might think there are quite a few, because we just give these loops some name. This is loop 1. It would be easier if we use the same color as the loop marking, the red loop 1. There's the red loop 2 and the red loop 3. But what about 1 plus 2? Okay, so I have one loop over here and have another loop over here. So in fact, the green loop is exactly 1 plus 2. It took two smaller loops and combined them into a larger loop. And in this process, something canceled out, because in V1, in loop 1, the way I drew it clockwise, it was this direction. In way 2, again clockwise, I went it in the other direction. So they are canceled. So I don't have to traverse them. It's one this way, one that way, and if you add them up, you cancel them. So it's the rest of the element. And that's exactly what happens when you're writing the equations. In fact, the 3, what I call fundamental loops, or just the smallest loop that cannot be decomposed into some other loops, there are 3 of them. And in this particular case, you can combine them any way you want. You can do 1 plus 2, you can do 1 plus 3, you can do 2 plus 3. You can even have 1 plus 2 plus 3, or none, which is a degenerate case, of course. But if you have 3 components, you can have any of them. By now you should know that there are 2 to the 3rd combination. I have no loop whatsoever, have just 1, just 2, just 3. You know, if you can write, this would be the representation. This means, do I have loop 1 or not? Do I have loop 2 or not? Do I have loop 3 or not? Okay, so 1, 0, 1, would be a loop that contains 1 and 3. So because this has 8 different combinations, you have 8 composite loops. 0, 0, 0 being a degenerate, I'm not going around anything, so my equation is nothing equals nothing, which is not very useful. So really, you can write 3 linearly independent equations. Okay? Linearly independent equation meaning any equation cannot be achieved by scaling or adding other equations. So for instance, if x1 plus x2 equals 0, that's a good equation. Okay, you have no other equation to construct this equation from, then that's obviously a linearly independent equation. But the minute I already have the equation and I was given 3x1 equal plus, or let's say equal, doesn't really matter, minus 3x2. Okay, is this a new equation? Yes, I mean it's new, it's different from the first equation, but it can be obtained from that equation by simply multiplying 3 on both sides. And then do a little movement, moving the x2 term to the right. So this equation is not new. It can be constructed from, linearly constructed from that. So you can write, therefore, 3 linearly independent equations. And you can verify this, that's what you can get. So now you have a whole bunch of unknowns. You don't know what's V1. By that I mean the voltage across resistor 1. And you can look at the way these signs are set up, and you know that I'm assuming V1 is this, how much it is higher from top to bottom, and so on and so forth. So I can write these 3 equations. But how many unknowns do I have? I have 5. I want to know the voltage across them. I have 5 resistors. So 3 equations, 5 unknown. This is not fully constrained. You have infinite number of solutions. There's so many different ways the circuit can work that will not violate KVL, the Kirchhoff's voltage law. So that's not enough. What else do we know? Well, that's KCL, Kirchhoff's current law. And that's really, again, just conservation. If you have a node being circuit elements coming together, multiple circuit elements coming together. So I may have, they're usually in plots drawn as a bunch of wires connecting together, right? But really wires are just for visual purpose. The circuits consist of these elements, these resistors, battery or voltage source and stuff that we will see later. And the wires are there to connect them. Wires have 0 resistance. These are ideal wires in these ideal circuit diagrams. So really, there's no voltage across them. You can draw as long as you want. It doesn't really matter. It doesn't change anything. When multiple circuits come together, the current that comes into this node is the same as the current that comes out of it, okay? Which is, again, just merely stating conservation. The electrons, if you have a frame over here and count the number of electrons, then the number that comes into this frame is the same as the number that goes out of this frame in any time period. It doesn't accumulate. This is the node where there's nothing. We're not talking about some device. Okay, so this the total current that flows into this node or a device, because it's connected to the node, it's the same as that goes out. If I have multiple devices connected, like that, then there is perhaps more than one coming in, and there's perhaps more than one going out. But again, it needs to be balanced. The circuit, the diagram, the circuit represent all the possibilities where the electron can go. Again, if you have, let's say, a leaky wire because the insulator part is gone and it's connected to ground, you have to draw it. You basically say, oh, there's another possibility going to ground. That's a different story, okay? So in the circuit that we draw, we consider that's everything. So if you have a node and you have these currents, if we can clear this bit, in here we know there are 3 currents. We can draw another current in here. Let's call that current. We don't know what the current flow is, but it doesn't matter. I'm going to call this, I think I5 is left. So I'm going to call this I5. Now, at this node, we know that I5 is coming in, I4 is coming in, and I3 is going out. So then I have that equation. Similarly, if you look at this node over here, the one that we marked V2, we have I1 coming in, I2, and I5 going out. And here's the point. If you have a node, if you treat this whole thing as a node, you can do that. You can consider as this circuit element, the resistor, the 4 ohm resistor is connected to this node. This other resistor is connected to that node. Connecting to that, there are 4 circuit elements, 1, 2, 3, 4 here connected to this super node. The same thing would apply. Who's coming in? I1 and I4. I1 plus I4. And that has to be equal I2 plus I3, which are going out. But I have a super node consisting 2 nodes, V2, V3. If you look at this equation, these 2 equations, what do you see? If I add them up, the left-hand side and right-hand side both have I5, they cancel out. The left-hand side therefore becomes I1 plus I2, I1 plus I4, and the right-hand side I2 plus I3. So a supernode is merely repetition of conservation principle. Okay, if the current is conserving at node 2 and 3, if we treat node 2 and 3 together, it still has to conserve. Okay? Not very difficult. And these laws are really why you have the equivalence model that you probably still remember. They're corollaries. They're not new insights. So let's say series resistors. Why? Well, if we look at these 2 resistors and treat them as one single resistor, what is the voltage across them? Because they're connected in sequence, in series, V is V1 plus V2. Okay? And what is the law that we apply here? Look at this node over here. Current that comes into this node is the same as the current that goes out of this node. So, because it has nowhere else to go, the I is the same I. So this side, it would be I, R1, I, R2. These are the same as V2. That's your Ohm's law. So V, which if we call that an equivalence, RE, it's this. If we cancel I on both sides, the equivalent is R1 plus R2. Okay. Similarly, why do we have parallel resistor that is 1 over R added over another 1 over R2? That's the parallel equivalence. That's because V is the same over here. Okay, so the I at this node shows that I is I1 plus I2. And again, applying Ohm's law, what is the I1? Well, that's V over R1. And I2 is V, sorry. Let's erase that. V over I1, R1 is I1. V2, V over R2 is I2. And this is, if we take this as an equivalent, oops. Have to write this again, V1 plus V over R2. And if we treat the whole thing as an equivalent resistor, then its V over RE has to be that. That's the current. Okay, you cancel out V, then this is what happens. So this model, of course, allows you to simplify the circuit, to compute what's happening, but really they're just derivation of from the basic laws. Okay, so now if we have this circuit, the one that we saw before, how many KCL equations can you write? Linearly independent KCL equations. Because if I have a node over here, I write an equation. I have another node over here, I write another equation. Of course, I can write a supernode equation consisting these two nodes. But that would be uninteresting, as we saw. They're merely the sum of the two independent equations. So how many? If you haven't done this, pause the video and think about it. So 4 is a very common answer, right? I have one node over here, one node over, let's call them 1, 2, perhaps there is another node over here, 3, and there's another node over here, 4. Okay. Is this a node? No, because it's uninteresting. There's no circuit element. It's the same as node 3. Anytime you have a wire, they're all idealized in the circuit, you can cut any segment of wire and just stitch them together if you wish. So I can imagine this node over here, this little wire is all gone, so I'm just going to move these two together. You know what I mean? So so it's the same node. So we have 4 nodes, but the answer is we have 3 equations. The reason is, if we have any nodes, let's perhaps clear this, we can add them up, but if I have 4 nodes, we can add all 4 nodes up. So 1, 2, 3, 4. What if we wrote the equation for all 4? I'm not going to do it, you should. If I wrote the equation for all 4 and I add it up, I add them up, I add all of them up, what do you think the equation is? You can imagine that. That would be a supernode that contains all these nodes. Who else is a circuit element that is not included in that supernode? Nothing. If we included all the nodes, then all the relevant circuit on that graph, on that circuit diagram, are included. So this becomes a supernode where there is nothing outside, so necessarily that equation is going to be 0 plus 0 equals 0, which means if you write the 4 equations, that would be something like that, and you can check. Everything must appear in pairs. I0 minus I1, I2, I3, I4, I5. So when you add them up, it's 0 equals 0, which means if you give me any 3 equations, 1, 2, 3, 1, 2, 4, 1, 3, 4, any 3 equations, I can tell you what the next equation is by simply adding them up on both sides. And subtract 0, subtract the thing from 0. So it's not a new equation. You can eliminate any one and still get the same amount of information. So there are really only 3 equations. But in this case, if we look at it, we have 3 equations from KVL. The 3 equations that we just got, KCL, we have 6 equations. How many unknowns? Well, we're writing a whole bunch of weird things, right? We have I's sometimes, we have V sometimes. So if we can take the leap of faith, it's not really a big leap of faith. I is the same as V, not value-wise, but in terms of unknown. Why? Because I is a constant away from its V. So they're really the same thing. So then we have lots of I's. We have 6 I's, 5 V's, right? So altogether, we have 6 unknowns. Because the V's can always be, any of these V can be translated into, oh, what is the resistors of R1? It's 1. So convert that to I1. So if you think about it that way, we have 6 unknowns. I0 to I5. 6 equations, 6 unknown, great. Another way to think about it, okay, I have 6 I unknowns, I0 to I5, but I have 5 V unknowns. You might wonder why that's the difference, because I have a voltage source over here, where I know it's V, but I don't know it's I. Everything else, V and I always come together. So if you look at it this way, then I have 11 unknowns. I only have 6 equations, but that's because I can write 5 more Ohm's law equations. So no matter how many ways you look at it, you can solve this problem. Okay? In real world, or once you get more comfortable with it, do you really write so many equations? The answer is no. Sometimes when you get, let's say, very comfortable with solving the equations, you can add things to say, let's treat A as a voltage. Let's call A a voltage, a potential, VA. So that's an unknown. VB is an unknown. If I look at this, I can get current all I want because all the elements, the voltage is fixed. It's 14 volt over here. That's what I know. Then the voltage across this is 14 minus VA. The voltage across this is just VA. 14 minus VB. Across this, that's VB. This is VA minus VB. So I can write current for every resistor in this by just having 2 unknowns. And the equations would be something like that. I can write a current VCL, KCL equations in 2 equations, and I solve my circuit. And there are many tricks. In 113, they'll explain that to you. Okay, so I'm not gonna go through the detail. So these are linear circuit. There are lots of ways to simplify them, so that you might ask, what is a linear circuit? That the response is a linear function, let's say current. I increase my voltage, then my current increases linearly, which is not true for a nonlinear circuit. You may see something that goes like this. This is a diode. So when the voltage is low, you have very small circuit current, and once it passes a some sort of a threshold, and the current is very large. It's essentially a conducting circuit. You can say the resistance is very small, or even idealize it to 0. And so that is tricky. So linear circuits are simpler, but still you will go through lots of exercises in 113 about them. Here, what we wanted to tell for you to get a feeling is, if I put circuit elements like that, like the diagrams that we show, then because of all these laws, the physical law, the nature, the conservation, it says the circuit has to operate at a certain level, that the voltage be this, the current be that. And the way to figure this out is to write the equations and solve them, okay? To figure out what the constraint made the circuit look like, okay? Why do we have all these elements like resistors? Sometimes that's not because we built circuit with resistors. Like, it's not we want to put a resistor there. The only time I can think about having a resistor there for an actual purpose is to build a space heater. We need to convert the electric circuit power into heat. But there are lots of times where we have resistors in our circuit. And in fact, if you think about building a contraption like what we've shown here, right? Why do we build these gadgets, these automated systems? Really, we're lazy, to be honest. We don't want to do the boring labor, so we want machine to take care of it. And switch is a very useful thing. And we will see, in fact, the entire computer is built upon a bunch of switches. So what is a simple switch? It's a three-terminal device connecting 2 points by the control of the third. And if the control says switch on, it's conducting. And if the switch says off, it's high resistance. Let's say very high resistance. Then your light bulb is not going to turn on. It's not going to shine light. So those are switches. And how do you build them locally? I mean, from ground up. In fact, this is the stuff that we're going to explain a little bit next week. But here's a quick preview. That's when you hear the term semiconductor. Okay, it's a material where it's usually based on silicon. This material is not quite metal, not quite insulator. It can be manipulated dynamically, in fact, to act both as a conductor or to act as a conductor in some cases and insulator in other cases. The way we achieve this is to have silicon. Usually it's doped, but you will hear the detail in other classes, with an insulator to make sure that the control, which is on the top over here, doesn't get directly into contact with the circuit, meaning this control is not short-circuited so that the current flies into these control. Okay, so that is the metal part. That's the M. The insulator part, usually it's silicon oxide. That's the O part. And the semiconductor. So that's where you get the term MOS. And there are field effect transistors. We'll get into that. So these are basically, we turn the voltage, let's say high, and something happens. We have electric field, and this draws electron close to the top of the semiconductor, where they cannot go through because of the barrier, the insulator over here. And because we have more electrons in this region, in this darker region over here, and then the semiconductor becomes more acting like a conductor. There's more electron, free electron. And then if you have a voltage differential, then they start to move, and this is when they conduct. So that's roughly what it is. And it's oversimplified. And next week, we will explain more about this, and more importantly, how do you build interesting logical devices. So that's a snapshot of metal oxide semiconductor field effect transistor. That's a mouthful.